Thank you, Fred. Thank you all for turning up today and having putting some aside some time to talk about reliability making you some more money. Reliability making money. Number two. Now, last month I talked about a scenario where essentially being dumb was expensive. And if you recall, for those of you who were there last month, it doesn't matter if you weren't. I'm going to quickly go over what it is we covered last month, because we used a very interesting example. And that example was a monster of a mining truck, a truly huge mining truck, a really big one, 400-ton payload. It's a monstrosity. And often these trucks will be driven on site non-stop. It's a driver who comes in and comes out. And you can see how big they are just by the nature of that ladder next to the radiator fins at the very front of the truck. And these things can cost between $5 and $6 million, depending which model you want. The bigger, the more expensive. The more functional, the more expensive, obviously. And at the heart of these trucks, we have a very impressive thing. We have an engine which is of itself a very, very large machine. Now, this engine in particular goes beyond what most of us engineers are faced with on a day-to-day basis in terms of scale and power. So this is a 20-cylinder engine, and it's obviously not cheap. It costs between $700,000 and $800,000. And so the question we were asking ourselves last month was, how many spare engines do I need to make sure I can get through a 3-year period just for one truck? And we went through a few scenarios. We're not going to go through all this again, because that was last month's webinar. And it turns out that if you use sort of textbook approaches to working out how many spare engines you need, you will almost certainly have too many things on your shelf. In the case of our truck, we looked at a real world example where the textbook approach came out as suggesting that we needed to have 5 spare engines to get through a 3-year period. But when we were smart about it, we actually looked at how our engines were failing. We were able to work out that we could actually not get away with 3. We only needed 3 engines. So if we use a textbook approach, we would have had 5 engines on the shelf. We would have almost certainly gone through much fewer than 5 engines, and had, after 3 years, 2, perhaps even 3 engines sitting on the shelf, deteriorating. These engines are impressive bits of kit. They shouldn't be left for a long time by themselves. They need to be maintained. That too is expensive. And often our mining sites are in far-flung corners of the world, which means that warehouses that need to be built in the jungle are incredibly expensive, especially if they need to be temperature controlled as well. So a lot of companies I work with, for whatever reason, use the textbook approach to working out how many spares you need. Almost certainly are throwing money away when they do it. So what we're going to do this week is look at our engine, but in a slightly different way. All this webinar is me taking a break, because I'm going to ask you, the attendees, to do all the heavy lifting for me, to look at some stuff we're about to go through. And I want you to tell me what it is you see, and from the perspective of how we can make better decisions regarding our truck, our engine, and product systems or services more broadly. So for those of you who were at the webinar last month, or those of you who weren't, if there are any questions about what I just talked about in terms of sparing and textbook approaches to spare parts analysis, feel free to ask them now. I'll happily answer any surface level questions. But if there's a more detailed question, or a question which requires a more detailed answer, I'll take that offline afterwards. But please don't be shy. Feel free to ask any questions as of now. Okay, not being overwhelmed with questions just yet. Last month's webinar must have been outstanding. So what we're going to do now is we're going to look at our engine in greater detail. And in the scenario I'm talking, I'm painting, the scenario I'm working with right now, this engine is an engine for which we have data. We have some failure data. So we know something about the reliability characteristics of our engine. This is typically how things work in the real world. We'll get something, perhaps we'll have some preliminary reliability ideas about how our engine or our spare part is going to work, but it should always be updated with what we observe in the field. Now I can see a question coming through. Did the textbook method of spare calculation last month use Weibull to estimate reliability and make a prediction? The answer, Aaron, is no. The textbook approach is all about the Poisson distribution, which at the root of the Poisson distribution is an assumption of a constant hazard rate. This is one of Fred's favorite topics, the idea of a constant hazard rate, which means that we are assuming that our engine never wears out, it never wears in. An engine that is 1 million years old is just as likely to fail today as a brand new engine that comes off the production line. And we know that to not be the truth. And if we take the time to do, as Aaron suggests, do a Weibull analysis, look at the failure characteristics of our engine, we can make better decisions. And when we did that last month, I should say, not last week, when we took the actual characteristics of our engine into consideration and not a textbook assumption, we only needed 3 engines. So we saved at least $2 million up front, and then probably had many other line items of savings as well through warehousing, transportation, maintenance, all that sort of stuff. So the main issue with textbook approaches to spare parts calculation is assuming a constant hazard rate, which comes back to what we're going to look at today, which is focusing on how our engine or our system or our product actually behaves in the domain of reliability. Now, sorry, before I move on, Aaron, did that answer your question, or do I need to elaborate any further? It's all good, then it is all good. Fantastic, thank you, Aaron. All right, so now we're going to look at one of my favorite little animations or representations, that is the random hand of failure. Now, this random hand of failure, I use this a lot, and I like using it because it always allows me to always emphasize that failure is a random process. But because something's random doesn't mean it's not predictable. So, for example, there are going to be material imperfections. There's going to be variation in manufacturing. There's going to be seasonal weather changes. There's going to be variation in how our people or customers use our thing. That's possibly the biggest source of variation. But suffice to say, there's lots of things that combine to introduce uncertainties and variation in our product, system, or service, which means that we can't schedule in failure. Failure will never occur at a precise usage period from the time we open its packet or a box. Now, in this case, we have some data points for our engine, and these are the actual data points. Each one of these points represents the time to failure for a single engine. And you can see perhaps they tend to be clustered around 2 regions, one at the start, one at the back. But we need to provide some more context for this data because there's way more to it than this. So what we can do is plot this data on CDF axes. Now, a CDF is a cumulative distribution function. Cut a long story short, it represents the probability of failure. So as things get older, the probability of failure increases, obviously, and eventually the probability of failure will approach 100%. Our engine will almost certainly not working 1 million years from now. So the CDF value 1 million years from now is going to be 1 or 100%. That is what the CDF or the cumulative distribution function represents. You've got other webinars and articles which take you through that basic statistical function in a very easy introductory way. So if there's any further questions about what a CDF is, please scour the Ascendo website, and I'm sure you'll find something that helps you along the way. Now, on this particular chart, we have 28 times to failure. What I can't represent on this chart are 50 right-censored data points. Now, what is a right-censored data point? That is a data point where where the thing we are looking at was removed from the environment, the test environment or the operating environment, before it had a chance to fail. So what does that mean in this scenario? We have a total of 78 engines that make up our data set. 28 of those engines failed before we took that engine out for whatever reason. 50 of those engines were removed at various stages of their lives for, again, various reasons. Sometimes those data points are simply an engine that's been in a working truck at the time our analysis is conducted. So we have 50 engines that hadn't failed in a wide range of intervals. Some of these intervals are as low as 500 hours. Perhaps that truck, that engine had only been operating for 500 hours when we took a snapshot of this data. Sometimes we had to take engines out because a truck needed to be returned or otherwise retired. So that engine hadn't failed during over a certain interval, and that makes it what we call right-censored, because the time to failure is to the right of that data point. So we cannot ever exclude right-censored data points, because that is part of information that we have to deal with. I can see a question or a comment coming, I suppose. Nelson suggests that the right-censored engines are censored that are still running, not failed, parked, or met the achieved life. If that's a question, you've nailed it correctly, Nelson. That is what a right-censored data point looks like. It is a product, it's a router, it's a motor, it's an engine, it's a fan, it's whatever it is you're studying, that at the time your data analysis commences, that thing has not failed, but it still has really useful information. In fact, we can never exclude right-censored data points. And I'm going to ask, before I move on and ask you guys that question, Nelson, does that answer your question? No worries, thank you. So, given that we have got 78 data points, 50 of them are censored, why can't we just exclude the censored data points? It would make statistics a lot easier if we only had times to failure, as you're about to see. Why can't we ever exclude our 50 right-censored data points? Any suggestions as why we can't exclude them from consideration? Any ideas? The CDF come up pessimistic. Are you able to elaborate on what pessimistic means to you, Nelson? I can see Sean's got an idea, but I'll just let Nelson go first. I think you're on the right track. I just want to understand what pessimistic means. And Sean, you're absolutely right. Right-censored data is still valuable, but there's something bigger than that. That means we need to keep it. So Nelson says that the failures will be lower than what the actual reliability will be. You need data on failures and successes. What I think you're getting at, Nelson, is that if you exclude right-censored data, you are by definition excluding, or more likely to exclude, engines that have, for whatever reason on that day, longer times to failure. If you exclude all right-censored data, the engines that fail early are more likely to get through into your data set. And that's what we call bias. So if we exclude any sort of censored data, we are introducing bias into our data analysis. If we exclude right-censored data, we do what I think Nelson is suggesting, is that we drive the apparent times to failure down. The engines that have failed early are almost guaranteed to get into our data set, where those engines that are going to last for a long time, if our test finishes after 6 weeks and we exclude right sense of data, they'll never make or influence our data analysis. So we need to always include censored data, because if we don't, it introduces bias. I can see that if several items are still operating at high operating times, as Sean suggests, the characteristic life will be higher, which I think is rephrasing what I'm saying, that if you exclude right censored data points, you will essentially bias your data set towards engines which have failed early, which will mean that the apparent characteristic life or mean time to failure will be much lower than it actually is. And by including our right censored data, we make sure that our characteristic life is higher where it deserves to be. So we can never do data analysis without excluding any right censored data points or any censored data points. But I'm highlighting just how much or how many censored data points we have here. You can see that our highest, our last data point occurs at about 80% CDF. And we're going to talk about where we get these points very shortly. Are there any questions about what censored data is before I move on? There's no questions, and we're going to move on. Those are some really good feedback too. Nelson and Sean, fantastic. All right, so what I'm doing now is I have just taken that data and I have squished the axes, so to speak. What does that mean? I've created a Weibull plot. So if we look at that animation again, see what I've just done. If we plot our data on a normal or uniform or an absolute CDF, you can see when we skew these axes, so we have a logarithmic scale on the horizontal axis and we have this weird CDF scale on the vertical axis, we can do that in a way where it creates a Weibull plot. Now, I have done webinars on what a Weibull plot is as well. So if this is something that's new to you, I highly recommend that you go to my Weibull plotting webinars to look at what a Weibull plot is, because they are so useful. And we're going to use and leverage some of that information in what we're about to go through right now. You should be able to keep up if you've never heard of a Weibull plot before, but I cannot suggest strongly enough, if you've never done Weibull plotting, or if it's something you're not completely familiar with, or if some of the things we do today make you think, I never knew you could do that from a Weibull plot, then please go and look at our Weibull plotting webinars and some of our articles to learn about how a Weibull plot can be really leveraged to help you make some really cost-saving decisions. So the question I'm going to ask you guys right now is, should I schedule my engine to be swapped out? So let's go back to our data. Now, you can, for those of you who are familiar with a Weibull plot, you can see on the top left-hand corner of our Weibull plot, we have a sort of weird angle scale. We have a bunch of numbers at the top where you can see there's sort of different slopes. Those different slopes point to a different value at the top. Again, you'll need to be across what a Weibull plot is to fully understand that. But suffice to say, these slopes give us an indication of what we call a shape parameter, the beta parameter of our Weibull plot. And the beta parameter is a number on the top of our scale. So if you can have a look at the data on the screen, you hopefully be able to see the numbers at the top. If you could imagine the line of best fit, or imagine the sort of typical slope of the data points, the curve, the CDF curve in a Weibull plot, can someone throw my way their best guess at what number aligns with the slope that seems to be the best fit for our data points? So, for example, if you think, let's think of one that's not right. So you can see that at the top we have a number 6. If you think that slope, that line, that shaded area which points up to 6, that slope, that angle, if you think that characterizes our line of best fit, then the answer is 6. Now I can see a couple of answers coming my way. Evan suggests it's 0.8. Eric suggests it's 0.7. We've got Striverson suggests it's about 3. And you know, none of you guys are really wrong at this stage, because it's your subjective assessment. And you can see that our line here has got some bends and curves and stuff like that. Someone thinks it's between 3 and 6. Looks like 2 populations. Interesting. Paul, I like your response. We're going to come back to that one in a tick. But if we were forced to draw a straight line through here, I'm going to put you out of your misery and suspense for a little bit, because it turns out that the typical slope for our engine, based on the data we have, is around about 1. So what does a beta parameter of 1 mean for those of you who have done Weibull plotting before or listened into our Weibull plotting webinars? What does a slope of about 1 mean, notwithstanding there's a bit of some funky curves going on with our data points? Constant failure rate, says Sean. Random fail means says Mark, I think you're talking about randomly occurring with respect to usage, as in it's not going to be more likely to occur early, less likely to occur late. Just be aware, even wear out failure is still random, but I think I take your point. But we've got a bunch of people who say exponential failure rate. I can see we have a very learned audience today. Now, if we have a constant hazard rate, and let's just assume that for the sake of this question, it is a constant hazard rate. Remember, the question I ask you guys is, should we schedule our engine to be replaced at some sort of fixed interval of time if we have a shape parameter or a beta parameter of 1, which implies a constant hazard rate? No, great answers. Based on the premise that our thing has a constant hazard rate, which means it never wears out, it never wears in. An engine that is 1 million years old is just as likely to fail today as one that is brand new. From a statistical perspective, if that's truly what's going on, then we should never, ever replace our engine. And we know that's nonsense. But the reality is, if you were to plug these data points into software that does some stuff, it would suggest that the hazard rate is constant, because the single line of best fit that Weibull software tends to do has a shape parameter of about 1. So straight away, if we were to do a traditional approach to Weibull analysis here, we might be incorrectly suggesting that we should never swap our engine out. So the next question I'm going to ask you guys, and I like Paul's response or Paul's question, that it looks like there might be more than 1 population. So next question, what might be driving failure? All right, so if you look at this line, these data points here, Paul suggests there might be 2 populations. Paul, would you like to elaborate on what you mean by there being more than 1 population? And I'm acknowledging Mark's responses as well. Yes, you raise a good point. You only replace if you have high beta, which implies wear out. Replacements are a big mistake if you have wear in. Essentially, you're resetting the wear in period again, and perhaps you can see 4 populations. So, Paul, are you able? You might be furiously typing away. Let's see. Oh, let me. So Paul, you said because you see a knee in the curve. Okay, so next step, for people who don't know what 2 populations are, what do you mean by 2 populations? I agree, I can see some weird S-shapes going on, but what is at the heart of this S-shape in terms of 2 populations? Perhaps up to 4. There are multiple failure modes, or lots. I prefer to say multiple failure mechanisms, because failure modes are the manner in which something fails. Is it leaking heavily or is it leaking slowly? And failure mechanisms are things that we can model because it deals with the physics of the problem. But I completely agree. There are appear to be at least 2 different types of failure processes going on. And when you have 2 different types, that means you see especially in Weibull plots, different slopes. Weibull plots are really good at modeling single failure mechanisms. Really, really good. They're very useful, which is why Weibull plots are used so much in reliability engineering. But if you have a complex system, and hopefully you all agree that an engine this big is a complex system, you are going to have different ways your thing can fail. And I can see that Stuyvesant is voting for 3 populations. All right, so let's just scratch that itch for a little bit. Let's have a look at our data in greater detail. What I have done, this is real data by the way, is I have looked at the 3 most troublesome components, and these are now represented on our CDF plot here, our Weibull CDF plot, with different markers, different colors, different shapes. We have red triangles. We have a yellow or orange cross. We have a green square. But we're going to look at our red triangles first. Now, what do you notice about where our red triangles sit on our CDF plot? Are they occurring early? Are they occurring late? They're scavenge pump failures to be specific. What do we notice about they're occurring late? Good work, Stuyvesant. They are the failures that occur at the back end of the apparent service life of our engines. And Michael points out these have a higher slope. And in fact, if we isolate these in greater detail and actually create a Weibull plot of nothing but our scavenge pump failures, we get this. Now, hopefully you'll all agree that that creates a relatively straight line in our Weibull plot, which has a pretty high slope. And what does high slope mean? Wear out, constant hazard rate, or wear in? Which one of those things does a high slope mean? Wear out failures. Fantastic. We see a really steep slope. In this case, it looks maybe higher than 6. If it's greater than 1, we know we have wear out. And so these could be the things that are driving the wear out of our engines. Now, I have spoken last year about data analysis, and I'm an advocate, I advocate against blind use of off-the-shelf software packages, and you're about to see why. I went and did let's say an accurate reliability analysis. I use a really cool Monte Carlo simulation approach where we actually sample from the true likelihood function and don't make those tons of assumptions that most off-the-shelf software packages make. And when I did that, I got this region here, our 95% confidence interval. This confidence interval tells me that based on the data for our scavenge pump, I'm 95% certain the true CDF curve goes through this region here. And you'll see that that doesn't really line up with our data points. Why might that be the case? Does anyone have any idea why the data points as plotted on this Weibull plot don't really line up with the essentially true analysis of all the data points we have in giving us our confidence interval? Mark has got it right. Many suspensions in the data, many censored points. What that means in practice is when we have interval data, when we have censored points, it makes it infuriatingly difficult to try and estimate the CDF of a particular failure point. So remember, we have 78 data points. Here we have 1, 2, 3, 4, 5, 6 times to failure for our scavenge pump, which means that we have 71 right sensor data points for our scavenge pump. And that makes it very difficult to estimate the CDF value of each time to failure for our data point when we have that much censored data. So if you were to do a simple Weibull plot, you will see that our data points don't line up with the true representation of our understanding of where the CDF curve should be. And this is going to become more prevalent later on. So just as a quick sort of summary of all that gumph, commercial Weibull plotting software sucks. It makes tons of assumptions, and you can make some really bad calls potentially if you forget that these assumptions exist and you have lots of suspensions. Suspensions really make it challenging to plot data points on anything. It's a lot easier when you just have times to failure, nothing else. But when you have that many suspensions or censored data points, it becomes a problem. Okay, so the line of best fit from the algorithm which I use to create this 95% confidence interval looks like this. And again, it's removed from our data points. And when I move this over to our scale over here, when it gets there, it suggests that we have a beta parameter of about 8.96. So it's much higher than 1. Now, given that you know this, what would you recommend for our engine, given that you know that we have essentially these tail end failures, these late occurring failures, mostly caused by the scavenge pump, and it has where our scavenge pump seems to be wearing out at a very particular point in time. That's what a high beta parameter means that when it does wear out, it wears out quickly, which essentially means it's the degradation mechanisms are highly correlated to usage as we've measured it. So what can we do? What can we make as a suggestion to our team to make things better? Eric suggests a scheduled overhaul or replacement based on run hours at that point in time, which is fantastic. We need to explore that further to make sure that's the right call. But had we just stopped at our system level analysis where our software told us the shape parameter was 1, we would never have got to this potentially cost saving recommendation of Eric that we actually schedule our overhauls based on this failure mechanism here in our scavenge pump, which is then going to then drive where we should either service our engines or replace our engines. And ideally, we don't want to replace an entire engine. We might be able to say, hey, if we can just replace a scavenge pump, we don't need to take the engine out. All of a sudden, we have saved huge costs in taking an entire engine out and replacing it with a brand new one just by servicing or replacing our scavenge pump at a set interval. Another thing that we can do, don't just jump to optimal replacement times. Maybe we need to get a better scavenge pump. Maybe we need to get a more robust one or design a more robust one, because if we can do that, then we can just address a teeny little bit of our engine to essentially make our engine act as if it doesn't have this wear out characteristic. So Shrivitson asks, how will you determine the overhaul interval based on this beta? Can you elaborate a bit on that? If I have time at the end of this webinar, I will. I also will point out that I have another webinar on optimizing servicing intervals, which addresses this precisely. Again, Shrivitson, if I have time, I'll have a conversation with you. If not, more than happy to schedule a conversation after the webinar. But as a third option, I do have a webinar where we address that servicing interval optimization bit. Cool. So what we've done now, just by scratching the surface a little bit, is because we were able to see from the start that we had at least 2 populations. As reliability engineers, we go, hang on, let's look at what's going on here. When we do that, we might have come up with a really cool recommendation which targets a scavenge pump and nothing else, but essentially revolutionizes our maintenance regime. Okay, so that's for our scavenge pump, which, as you might recall, seems to account for the few failures that occur at the end. And you can see that the uptick of the slope correlates with our scavenge pump failure data. Now, here is some bottom end failure data as well. Now, check this out. I've done use that really funky algorithm I talked about last year in my webinars. And here is our 95% confidence interval. And remember, because of all those suspensions, it makes it really difficult for us to plot or estimate the CDFs of our times to failure, which you can see here. It appears as if our data is creating a line which is completely unrelated to our 95% confidence interval here. You can see we have, let's just say, maybe 11 or 12 data points, 78 data points in total. So we have about 65 or 66 suspensions, which makes it really, really challenging. And so you really need to be on top of your game if you're going to use suspended data, and be very, very careful with off-the-shelf Weibull plotting software. So here is our line of best fit. And you can tell based on when we move it across to this slope up here, we have a beta parameter of about 1.11. So in reliability engineering parlance, that is pretty close to 1. So just to go over again what we talked about earlier when I asked you what does a beta parameter of 1 mean? What does this suggest? What does a beta parameter of a close to 1 suggest for our bottom end failure points? What does it suggest? You can see our data points re-embedded back in our overall thing. Exponential distribution, a constant hazard rate. Failures independent of running hours. Fantastic, Eric. Exactly. It is ageless. It never gets old. It never gets young. One that is a million years old is just as likely to fail today as one that is brand new. Now, of course, that's not always the case. Things will almost certainly deteriorate over time. But what that means here is that constant hazard rates typically mean that our thing is experiencing external catastrophic stresses. Why? Because think about a tornado. It doesn't matter how old or young your house is. If you get hit by an F5 tornado, it's going down. So the failure rate of houses due to F5 tornadoes should be independent of how old that house is. So if you're near Oklahoma or other parts in Tornado Alley, it doesn't matter how old or young your house is. The failure rate or hazard rate with respect to tornadoes is relatively constant because an old house is just as likely to be destroyed as a young house. Ain't nothing going to be standing after an F5 tornado goes through. And it turns out that after this analysis was done, they did a root cause analysis on the failures for our bottom end. I'm trying to get there, and identified that what was happening were these large contaminants in the lubrication. Contaminants would hit the metallic surface and essentially initiate a rapid deterioration of our machine, to the extent that each external stress from our contaminant was almost catastrophic. It would hit it, cause damage, and very quickly that thing would deteriorate. So that we can see here that our data analysis aligns precisely with what we expect, and that team was then able to go and make some changes in terms of the lubrication, the filtration, everything else like that, to remove what was another big part of the failure story for our engine. And we knew straight away from our Weibull analysis that it looks like there is a constant hazard rate. So that is the second of our 3 populations of failure. The next one is the valve train. Now the valve train has, here we have 6 data points. And it's starting to occur a lot earlier. I should go back 1 slide just so you can see where these orange crosses exist in the overall data set, if my computer lets me. So you can see here that we have a couple of valve train failures relatively early. Yes, there are a couple of late ones as well, but it's certainly not the scavenge pump, which seem to be having failures at the tail end and nowhere else. So if we do the Weibull plot for our valve train and valve train only, check this out in terms of discrepancy between the true confidence interval and the plotted data points, again, because of all those right-centered bits. Now, if you had those data points on a piece of paper and you were trying to manually fit the line of best fit, you would have all sorts of trouble doing it. In fact, in a way, the computer does as well, because this dotted line here represents the 50th percentile of our confidence interval. It sort of represents the point where we are 50% confident that the CDF is going to be higher or lower. So we often use the median or 50th percentile to characterize our CDF curve when we're doing Weibull plotting. The maximum likelihood estimate produces a slope like this, a line like this. And you can see that these lines have quite different interpretations when it comes to slope. And the reason why there's this big discrepancy is because of that censored data. Now, I'm talking about censored data as if it's a bad thing. It's not. It is something we need to include. We can't exclude censored data because it introduces biases, but we need to have censored data. So we need to have censored data. We can't exclude it. But by the same token, that really makes some of our computers struggle to accurately match up what's going on with what it looks like on our computer screen. So this confidence interval here is again based on the algorithm. So this confidence interval is spot on. This is the true confidence interval. If you have, has anyone experienced doing probability plots on any commercial Weibull plotting software where you have, in this case, 6 data points and 72 suspensions or censored data points? Does anyone have any experience where they've tried to do Weibull plotting with so few times to failure and lots of suspensions? There might be 1 or 2 of you out there interested to see if there have been. Yep, the confidence interval is extremely broad. Now, the reality is, when you do it correctly using this algorithm, the confidence bounds come in a lot tighter. If you do this on, let's just say Weibull++ or something similar, the confidence bounds blow out because off-the-shelf software involves 2 and sometimes up to 4 algorithmic assumptions. And when that happens, essentially those assumptions don't do well when we have censored data. And so you'll have weird confidence bounds, weird confidence intervals when you have data like this. If you're serious about trying to save millions of dollars from day one, you really need to get on top of modeling reliability data accurately and creating confidence intervals which are based on the actual data and not 4 or 5 levels of assumptions. It's all bad when you have just a few data points and off the shelf software looking at the likelihood functions of MLE and everything else. So some good feedback there. I haven't done this. I don't use off-the-shelf software because I have my own thing. But every now and then when I do get access to it, I use data like this just to show people how different the off-the-shelf software outputs are when compared to the true software outputs. And the true software outputs are often a lot tighter, a lot less uncertainty, and often help you make better decisions just by using the correct approach. Okay, so depending on which line of best fit you want to use, again, an issue with it comes to off-the-shelf software. Let's in this case use the maximum likelihood estimator, and we move it across. We have a shape parameter of about 0.73. Now remember, the 50th percentile line, the median line, had a much shallower slope. So it would have a beta parameter of perhaps about 0.5. So either way, we have a shape parameter or a beta parameter which is less than 1. What does that suggest for our valve train? What does that mean? We have a beta parameter which is less than 1 for our valve train. Wear in. Thank you, Sean. What causes wear in, or what causes infant mortality? Thank you, Shrivitson. What are some of the root causes of wear in or infant mortality? Generally speaking, I should say. Installation, manufacturing, excellent. Well, we have defects in a small number of the population because we have improper manufacturing approaches. Even having a 10% defective fleet of products is still a huge number, but essentially once those 10% fail, the apparent reliability of the remaining population increases because by definition, it is less likely for those remaining things to have that same defect. Some really good answers here. So in this case, when we fast forward, an RCA was done on our valve train, and these failures were typically all caused by installation issues, alignment issues. And so as a reliability engineer, how useful are you to your organization if you can just use this data and predict what the root cause analysis is going to find in a very useful way? How useful are you, or how valuable are you to your organization? If you're able to look at this data, take the 3 most dominant failure mechanisms, do what we've just talked about here, and say, hey, you know what? Our scavenge pump, it's wearing out. We've got a few options here. We can modify our maintenance regimes. We can perhaps even do root cause analysis on that scavenge pump, but it seems to be failing at a pretty consistent point. There's a very sharp or very high slope. When it does wear out, it seems to wear out very consistently. So it is very uniquely tied to how we measure usage, which potentially means that we don't have a pump which is robust enough. Or if that's the pump we have to use, then we can have a maintenance regime where we swap that scavenge pump and that scavenge pump only at a fixed interval, and our engines keep going. Think of our bottom end failures. If we see that we have a typically constant hazard rate, we know it's an environmental thing. So what's going to cause damage to our bottom ends and every other similar piece of metal around it? Well, lubrication is the likely culprit, or things in the lubrication. And so when you see constant hazard rates associated with things that essentially live and die by lubrication, it typically means that the contaminants in that lubricant are so big that when they do damage our thing, it invokes pretty rapid deterioration. Other contaminants, they more slowly wear things down over time. And which in a way, it's good that you see a constant hazard rate, because it typically means you have really big or really bad contaminants, and they're the easiest ones to resolve through having better filtration systems. And when it comes to our valve here, how useful would you be as a reliability engineer by being able to say from the data analysis and nothing else, hey, we likely have an installation problem or a manufacturing problem here. You can save months of root cause analysis by helping the team focus on what they should be looking at. We know our valve train is not wearing out, so we don't need to do any accelerated live testing. We need to look straight at manufacturing defects, installation, assembly, all those sorts of things. And so let's put our valve train data back into our overall data set. Okay, so before I move on to the most important message of this lesson, are there any questions or are there any comments? Or does any one of you guys have any similar experience you'd like to share with our fellow attendees? Any questions or any war stories? None. Cool. All right. So we've done a lot of math stuff, statistical stuff, but none of that is the most important message of this lesson, or this webinar, I should say. Oh, right, lesson there. Sorry, it should be webinar. It's not a lesson. The most important message of this webinar, and not lesson, is something perhaps even simpler but more profound than the deductions we've just made. So we got a couple of those stories coming through right now. I needed to allow more time for people to type. So Aaron suggests that the issues he's faced is that failure data is not easy to separate by a failure mechanism. It is bunched together. So if it's bunched together, I'm guessing, Aaron, that you are not able to look at, you don't have the data accompanying each data point, which allows you to work out whether it was a bottom end or valve train or scavenge pump. Is that correct? Right. So the story from the thing we should learn from Aaron's story is that when we do testing or gather field data, we need to gather the data, not just the data points. We need to understand what caused that particular thing to fail, or even if it was due to a particular component. Sometimes I've had to do very forensic data analysis where I only had data points and had to look through resupply data to work out which component was ordered at a point in time close enough to that observed failure point to assume that component was the thing that failed. It's painful, but if you can do that, then you can look at what is causing these different slopes and different knees and different bends and different S curves in our Weibull plot. If you don't have that, then you sometimes are in a bit of trouble, which Aaron correctly points out was the case for him. Fantastic. Now I see a question from Nelson. Do I have a recommendation on database approaches to separate the different failure mechanisms? Let's say you have incomplete history or parts not available and cannot say the failure was due to the failure mechanism. Good, really good question. And again, so beyond the, let's just say, second order forensic stuff where I look at the resupply data and try and guess which component was ordered in response to this time to failure over here. If you go through that, that is a pain, but it's also the best way of doing it for that particular scenario. And if not, the best thing you can do is then essentially group the data points. Now, what I do when I'm able to do this is I actually create, if I see, okay, there tends to be, it looks like there's 3 or 4 subpopulations here. Let's just say I'll usually start with 2. I run that algorithm I was talking about, and it then finds the 2 most likely combined Weibull distributions, where one describes population 1 and one describes population 2. Now, the good thing about that is it's up to the computer to work out which data point lies in which region, or which under each different model, I should say. I don't need to draw a line between the 2. The actual algorithm will work it out for me. It's more and more challenging when you think you have 3 or 4 subpopulations, and often that means you're overfitting lines. The computer is going to essentially fit lines to just natural variations in your data points. But where there's a couple and very distinct lines, and if you have a lot of data points, I always use the algorithm. It is really good at being objectively able to find Weibull curves which marry up with different regions. That's the first thing. The second thing is, if you don't have that skill set, or if you don't have the ability to do it for whatever reason, then you have to do it by best guess. Now, in this case, if we might not have been able to work at that the scavenge pump was the thing that was going to fail at the end, but our curve, if we go back here, if we're trying to work out where we should schedule our servicing, well, even though the line of best fit in overall has a shape parameter of about 1, you can clearly see the tail end of our curve is kicking up. So you can manually draw a line through the tail end of our curve, and it would have in this case, a pretty accurate shape parameter. And you can then base your decision on when you should schedule servicing or schedule replacement based on that part of the Weibull curve, the CDF curve. Because that's the thing that's going to drive your decision making. Everything else, which appears to have a constant hazard rate, that is nothing that you're going to address during a servicing or schedule. You don't fix constant hazard rate failures by replacing anything. It's the bit at the end. So even in this case, if you have nothing else, draw that line through those data points at the end and use that to work out where you should think about scheduling your servicing. You can see straight away that at about 10,000 hours, if you were to swap your engine out there, you're going to avoid all those wear-out failure mechanisms. So perhaps as a very rudimentary best guess, that's going to be the recommendation you make to your team. Now, I've seen lots of reliability analyses that don't even go to that level. They say, well, the shape parameter on average is 1, so let's do nothing. And all of a sudden, we have these catastrophic wear-out failures because we didn't look at the tail end of our curve. So there's tons of different ways of answering that question. Now, hopefully I've given you a couple of ideas, Nelson. Do I need to elaborate any further detail, or have I hit the nail on the head, or as close as possible to hitting the nail on the head as possible? Okay, thank you, Nelson. I see Shrivetson suggests that only non-quality failures can be plotted on the Weibull. If there are a lot of quality failures, then 50% is there any way in which we can extract useful insight from these quality failures? Now, the first thing I don't like doing is preordaining something as a quality failure, which typically means infant mortality or wear-in, because quality often refers to those manufacturing defects or installation errors. And essentially everything else is non-quality. Now, I'll disagree with that, Shrivetson, in that only non-quality failures can be plotted on the Weibull distribution, Weibull plot. Sincerely disagree with that. In fact, infant mortality, which is the hallmark of quality failures, will stick out very, very clearly. In fact, our Weibull plot for I think it was our bottom end, that was an example of quality failures, or the hallmark, I should say, of quality failures being visible on the Weibull plot, which is why Weibull plots are uniquely useful. So I don't know if I agree with your premise. So is there any way we can extract useful insight from these quality phase? Well, absolutely. We've just done it today. Again, I look at my, if you look at my servicing interval webinar, I essentially do that by creating an algorithm which separates the infant mortality, constant hazard rate, and wear out regions of our post-servicing hazard rate. And by doing that, we're able to make good decisions about where we should service. We're running out of time, Srivatsan, so I'm more than happy to expand on this answer in a separate conversation if that one has not answered the question adequately. All right, so let's go back to my most important message for today once I do this. All right, the most important message of today, of this webinar, not lesson, is that even though we have a very, very complex machine, hopefully you agree, and my computer allows it to come up. This thing is a beast. It's a behemoth. It's a very big engine. It has 20 cylinders, costs between $700,000 and $800,000 US. It has, as you can see by this picture here, this illustration here, there has to be thousands of ways this thing can fail. However, when we looked at the data, 82% of failures were down to 3 components. 82%. 23 out of 28 failures were caused by 3 components. So the most important message for today is the vital few. Everything you need to do as a reliability engineer has to focus on the vital few. We are often in awe of the complexity of things like this machine, this engine, which means that we want to pour through data. We need to go and we need to do complex data analyses, all those sorts of things. But perhaps just speaking to the maintenance guys and saying, hey, what components do you swap out more than anything else? Now, we don't need to do Weibull plotting for those guys to say valve train, bottom end, and scavenge pump. That accounts for 82% of all failures. So if you spoke to enough guys, you quickly walk away from that 10 minutes impromptu survey, knowing as a reliability engineer, it's the valve train, it is the bottom end, and the scavenge pump that you need to look at. And when we look at that, look at what that means statistically, those 3 things account for 82% of all the failures we have observed. So it's the vital few. The vital few is the most important message of today's conversation, because you can make astronomical improvements in reliability by always remembering that it's the vital few. It's 1 or 2 things, in this case 3 things, which dominate the failure for this very complex bit of kit. Now, it's not always just 3 things, but the principle remains the same. The weak points are the weak points. They're the things that are driving the reliability characteristics. So always, always, always focus on the vital few. Now, given that, I have a few more minutes left. Are there any questions about the vital few or anything else that I've covered today? Off-the-shelf software sucks. It has severe limitations. Any questions? Have I ever seen a mechanical failure caused by software? As in these engines have electronic brains? Absolutely, especially where you have, for example, excessive braking, where you have just recently worked with a military vehicle where it's had a problem with its ABS. And that meant that braking was occurring and not occurring when it should have. And this manifested itself in terms of faster than anticipated wear on brake assemblies and cylinders and everything else. And we couldn't work out what it was until we worked out the root cause was essentially the ABS computer, which means that we have an apparent mechanical failure but caused by software. So the answer to your question, Nelson, is absolutely, and it's becoming more and more prevalent as things become more automated. Aaron asked, you briefly mentioned about using commercial software. What common pitfalls should we be aware of using commercial software to do Weibull? So the first common pitfall is that the confidence intervals and the lines of best fit are often not the lines of best fit. You will often get in particular confidence bounds when you have either a few data points or lots of censored data points, even if you have lots of times to failure. The confidence intervals are always blown out, and you often see even on some of the propaganda / marketing pieces, marketing brochures for these bits of kit, you will see confidence bounds which sort of double back on themselves, which is statistically and physically impossible, because they have somewhere between 2 and 4 assumptions to quickly give you those confidence intervals. So if you have a few data points, and yes, 6 is a few data points, or if you have lots of data points, but lots of those data points are censored data points, you'll have confidence intervals which are massively blown out. And that means you might not think you've reached a milestone when you in fact have. If you were to do the same analysis using the proper algorithm, turns out you've got much greater confidence on time to failure than you thought, and perhaps that could move you through to the next step. I've seen lots of reliability data incorrectly interpreted as we have not arrived at our goal yet, and so let's go back and do some more stuff. It's wrong. It's painful, and don't forget, we're trying to make things more and more reliable these days, which means that you get fewer and fewer failures under test. So we have to deal with fewer data points. In a way, that's good. It means we're getting fewer failures. But when we do that, often the confidence intervals go through the roof and through the floor, and we make poor decisions. That's probably the biggest one. The other one is that when we have censored data points for our Weibull distribution in particular, you can get big discrepancies between the apparent slope of that line of best fit and the actual slope. So if I go back to I think our val train, when my computer lets me. All right, very slowly scrolling up, very slowly. So let's go to this one here. So you can see that the data points as plotted, because those data points, the CDF, are best guesses with all that censored data point. If you were to draw your line of best fit, you might actually conclude that the shape parameter is greater than 1, because the slope of those data points is a lot higher. But when we do the correct analysis, you can see that the slope of the true CDF is more likely to be much lower. And depending on whether you use MLE or the 50th percentile, you will get different interpretations of the slope. So if you have lots of censored data, you might get software which suggests incorrectly that your slope is higher or lower than it actually is, which could then lead to an entirely incorrect RCA, where you're investigating wear out, where it should be wear in, or you might think we're okay when we're not. So there are a couple of really big pitfalls when it comes to software. Perhaps the biggest one is that software often makes people stop thinking. We just put numbers into software, get an answer, and we don't think about we don't think about the process itself. That's probably the biggest pitfall, is that people just use software as an opinion generator, and when you get the opinion back in the form of numbers, finish your report, off you go. What's the next thing we need to do? And that's probably perhaps even the biggest pitfall of software, that behavioral issue. Okay, so I've seen Michael said a couple of things. Remember that if we don't change our direction, we're liable to end up where we're headed, which is a very good point. If nothing changes, nothing changes. So if you keep using outdated or inaccurate approaches, or even if you just simply, if you think about what we did today, if you didn't scratch the surface, if you just stopped at the assuming that our engine had a constant hazard rate, think of all the costs we would have incurred by not getting to the root cause of our valve train bottom end, and perhaps most importantly, our scavenge pump failures, because that scavenge pump failure was the dominant wear out failure mechanism. Okay, Nelson, more on Weibull. Or alternatives, how do you handle only censored data with a few, 1 or 2, or no failure data? Now, if you have censored data, with no failure data at all, you have a problem, because that means the maximum likelihood estimate for only censored data, only right censored data, will be an infinite reliability, or an MTBF, which is infinite. So if you only have right censored data, the only way you can estimate reliability is if you use Bayesian analysis and a prior distribution, which is a subjective assessment or subjective probability on the likely reliability characteristics of your thing. Yes, then right censored data can then update a pre-existing prior distribution. But if you are going to use classical statistics and use nothing but right censored data, it will automatically and always say that its best guess on the reliability of your thing is 1 forever, or an MTBF of infinity. So that's the first thing. With the second thing is that there are very few people out there who actually do the proper algorithm, or involve the proper algorithm to get the proper analysis for a small number of data points, and with lots of censored data. So I looked at reliability data analysis. I did 4 webinars last year. So the algorithm I described there, that's the sort of thing you need to do, because the assumptions that software makes, off-the-shelf software makes to get there is horrific in those scenarios where you only have a small number of data points and or lots of censored data points. So you need to find that statistical guy or girl or reliability engineer, someone like me, who is able to do that for you if you're not going to create your own algorithms. So that's the short answer. There's no commercial software out there yet which tackles this. If you need to investigate that further, go back to our data analysis webinars last year, and that describes what you need to do to get the proper and correct answer. Okay, I know we've 5 minutes past the midday. I'm more than happy to keep talking as long as Fred tolerates this and you guys want to talk. For those of you who need to drop off, I can see a couple have already dropped off. Thank you very much for your time today. It's always great speaking to you guys. One thing I'll always ask is that you give us feedback and comments about what we did well in this webinar today, what we didn't do well. If it's a good comment, put it on our comment box. If you've got any suggestions, feel free to reach out. Feel like to reach out to me or Fred directly. Shrivitson, I see that you just said that's an awesome push to build your own algorithm. Yes, there is. It is something that you could uniquely benefit from. Now, to be clear, there are scenarios where reliability off-the-shelf software is more than fine for what you need to do. I want to be clear about that. But the reality is it's not general. It won't be useful for every scenario. So if you're trying to deal with really reliable stuff, then you need to perhaps really investigate doing it yourself, or finding someone who can do this for you. Thank you very much. I think it's Mumtaz there. Nelson, thank you very much for your kind words. Rahul, how can I get to your earlier webinar? If you go to accendoreliability.com, you can go to our webinar page. I'm sure, Fred, if there's any additional guidance you want to type in, please feel free. But in our webinar series, I think as long as you become a member of Accendo, you get access to every single one of those historical webinars, and that should be, as far as I'm aware, still available as of today. And I don't think that's going to change anytime soon. So if you have a look at the accendoreliability.com website, if you have any problems finding those webinars after that search, please feel free to reach out to me. I'm sure Fred would be happy to help you out as well, but I can certainly guide you to where you need to be. There we go. So if you'll see in the comments box, Fred has given you the link. And he's highlighting the fact that these are free. Just as for those who are champing at the bit to get your algorithms done, just be aware there are a couple of problems with that. that you'll need to overcome, especially with these weirdly shaped likelihood functions. Essentially, the likelihood function, for those statistical nerds who know what that means, when you have lots of uncentered data, your likelihood hill, or the hill that looks like that defines your likelihood function, turns into like a massive boomerang, very narrow boomerang, which is very hard for most traditional algorithms to try and sample from. So you need to be pretty tricky in terms of trying to use traditional algorithms to get there. And so you often have to work on your own, but that's a topic for another day. I can see we're down to 14 attendees. Any last questions before we call it quits for today? Thank you very much, Robertson. Much appreciated. Thank you for your feedback and interaction too. When people like you interact with us, it makes it that much more exciting at this end at least. So thank you for your input as well. Do I employ MATLAB, C, or Python, or do I do my own coding? Now, Nelson, I do MATLAB, but I'm not going to advocate for MATLAB over everything else. The reason why I use MATLAB is because for a lot of I do a lot of training as well, a lot of interaction with people trying to illustrate concepts. MATLAB is really, really good at creating videos and animations of statistical stuff in ways that Python, for example, or R aren't. So that's the reason why I use MATLAB. But the reality is, all those other coding platforms you talked about there are just as capable. So I use MATLAB for my own reasons. I'll advocate for it because I think it's very, very useful, but that's because I also want to get some really cool videos of, for example, this simulation happening. If you see those webinars we just talked about last year, you'll see some of these rotating surfaces and some of these data points and random walks and things like that. MATLAB is just so much better than anything else at creating those those videos for these webinars and lessons, and that's why I use MATLAB. All the other platforms are really, really useful. All the other languages I should say are just as useful when you're trying to solve the problem. No worries. Thank you, Nelson, for your interaction as well. Okay, ladies and gentlemen, if there's no more questions, I'll call it quits there for today. Thank you for sticking through to the end. Hopefully you've got a lot out of today's lesson, webinar. And the most important thing is the vital few. That makes everyone's life easy. First, maybe the easiest thing you can do is speak to the guys and girls who take components out of your things that are failing too often. Ask them what's making their lives miserable, and go from there. You can often save yourself 3 months worth of analysis just by speaking to the people who are observing what's going on. But that's not to say data analysis is not useful. Hopefully you can see how powerful it can be. All right, so ladies and gentlemen, until our next webinar, have a splendid Tuesday.